Okay, we're going to build a spreadsheet now to solve this example. It's a backwater calculation. I'm just going to describe it slightly. We've got a dam. We're saying that this is 5 meters high, and this is in a long rectangular channel, so that's telling us what the equation is for the area weighted perimeter. And long is telling us that it goes to normal depth upstream. So at the upstream end is normal depth. And then later on, take at what distance is the water level not affected by the dam? So what that is actually asking is how far does it take for normal depth to be achieved? So yn is what we're trying to work out. So we're trying to work out this delta x length. I'll call it a delta x. We're actually going to use various little delta x's. Now, what it doesn't tell you in the question how many delta x values to use, but it does tell you in the answer how many. It says 2 steps of integration, and that's really meant for a hand calculation. However, with 2 steps you'll get that number, about 4.5 kilometers. However, with 10 steps of integration we'll get about nearly 6. So clearly 2 steps is not sufficiently accurate. But what we're going to do is build an Excel sheet where we can we'll have 10 steps of integration. Okay, we could in fact increase that number and see whether we get more accurate, or this length converges on a fixed value. Okay, we're going to do various things here in this example. We're going to build a spreadsheet from scratch. We're going to calculate normal depths. We're going to calculate critical depth. Okay, let's go. Right. The first thing to do is extract the data from the question and write it down so it's all clearly available. So let me just zoom out very slightly. So I've set up my sheet. I've set up my sheet so that I have yellow cells with my fixed data in, and I've got these beige cells which have got some intermediate solutions. First thing I've done actually is start with putting a value G in there, because G is quite handy, and you can refer to that cell, that B1 cell, if you like, every time. I've actually labelled that by typing G in this cell up here, so I can use the letter G in all my equations. You don't need to do that. What we need to do here is put in our values. So we've got a Q equals 10 meters per second, 2 meters cubed per second, B is 3 meters, N is 0.2, we've got a slope of 0.01. So I've got those in here, and I'm going to put those in, tight and precise numbers in here. 3 meters. Always put your units in the Excel sheet when you're doing it so you know what they are. We don't really use units for N. Okay. Right, normal depth. We're going to have to calculate normal depth because we need to know how many, what are our delta Y steps. Now what I'm talking about there. So we're going to do a step, 10 steps from this level. We're going to do 10 steps down here, delta Y's, from the 5 meter to yn. And in those 10 steps we'll get 10 delta x values, and the sum of those will give us the answer, this x distance back upstream until normal depth is achieved. Okay, that's the objective. Now, when you're constructing an Excel sheet, do write down all your equations and have them handily there in front of you. So I've written all the equations we're going to use. These are all the equations we would use in a backwater calculation. We have Manning's equation. Why do we use that in the backwater calculation? Because we rearrange it to get an SF. Okay. We also use it to calculate yn. That's what we're going to use first. I've written out the Manning's equation for a rectangular channel. Actually, we don't need to do that. If you set up your Excel sheet appropriately, you can just have entries for A and R in your Excel sheet and leave the Manning's equation the same every time. The main equation that we're integrating is this equation, and we know we've got to have SF. When we calculate SF from this equation, we need to calculate the Froude number squared, and the Froude number squared is this equation. I've also written it down here for a rectangular channel. Again, I think I prefer to use the main equation and just calculate A and B for a rectangular channel and put those in the standard equation. And this is the numerical approximation we're going to use. We're going to calculate all these terms at a mean value. We're going to have a mean, a y mean, and we'll see how we get to that. Okay, keep your equations handy. That's the message here. Right. The first thing we need to do is calculate the value of yn, because that tells us how many steps we're going to go down to get from 5 to yn. So no, it tells us the delta y. We're going to go down in 10 steps. So first of all, yn, how do we calculate this? So actually, I'm going to delete this lot. I've set up a little table and we're going to just work this out. Right, I'm going to choose I'm trying to guess y, because we've got to solve the Manning's equation here. So I'm going to guess a value of y. Probably should put that in meters, units, meters cubed per second. Okay, so put in the Manning's equation. So we've got the Manning's equation here. I'll use this rectangular one here. So that's going to equal, let's have this bracket b times, sorry, not b, let's choose the value of b. Here we need to fix that, times by y, all to the 5/3. We need to divide that by b, and we need to go back up to b here, fix that. No. Plus 2 times y, bracket all to the 2/3. We need to divide that by n, so we need to go and find n, fix that. Then we need to multiply it by the slope, all square rooted. Oh, we need to fix it first. All square rooted. So 1 gives us a Q of 3 meters. Well, what's the Q we're after? After meters cubed per second. We're after 10 meters cubed per second. So let's go back. So let's just put in an error value here. This is useful. We'll have this minus the Q value that we're aiming for, which is 10, and we fix that. So the error is, well, -6. Doesn't matter about the sign. We're interested in getting the number to this error to 0. Instead of doing a complete trial and error, just guessing numbers, what I'm going to do first of all is put a series of numbers in and see where the error changes from negative to positive. So I'll do the one before plus this delta y, so this is and I need to fix that, and then I'll pull these two down, and we see Q is increasing slightly, so that's probably right. So it's still 6 error. Let's just increase that delta y I'm choosing. Still, it's not getting the error is getting smaller, but not small enough. So let's have a 0.5. Okay. Well, let's just put 2 in as a guess here. Right, okay, so we're going down here. We see the error changes between negative to positive at this point. So the solution is here between a depth of 2.4 and 2.5. So if I put 2.4 in here, I change this to 0.01, we see now that the error, the error changes between positive and negative. At that point, the solution is between 2.3 and 2.4, and slightly closer to 2.44. So I could put in here 2.445, and I get an error of 0.04. I think that's 2.44 is good enough for us now. Okay, so there we have 10 meters cubed. So let's go up onto into here and put in 2.44 meters. Okay, I've got a cell in here for critical depth. We don't actually need to calculate critical depth, but let's just do that while we're at it. We can write a similar sort of table below here. I'll put in YC. That calculation is going to be the Froude number, and the Froude number equation is here just to my left. So that's going to be Froude number. Well, we knew Froude number squared. Okay, that's good enough as well. Remember, we're going to equate the Froude number to 1, so we can do this with the Froude number squared. So here, Q squared, which will be 10 fixed squared divided by B, which is 3 fixed squared times by G, and that's where I can put G in because it's on this worksheet. Sorry, I'm not going to times it by, I'm going to put a negative divide by, and divide by the number we're guessing, all cubed. So we're aiming for this to be 1, and it's way out, 2.4. Well, we know it's going to be less than 2.4, so let's just put this down at we know it's less than 2.4 because it's subcritical. Let's try 1. Oh, 1 is getting close. So this is negative though. So let's see about adding the 0.1 onto it and see if going deeper is well, it's the right direction. Else we can just change that. So it's getting towards 1. Sorry, that error is wrong. We need to take that's not taking 10 off, that's taking 1 off, so the error, let's get okay, so we've now got we can now pull those down, and we see that between 1.04 and 1.05 the sign changes. So the 1.04, we've got a Froude number of 1.008, so I think 1.004 is the appropriate number for critical depth. So we're going to write that down in here, 1.04 meters. So we've now started the calculation. We need to work out a delta y. I'm just writing in as capital. So dy delta y, this is I need my pen here, delta y. Okay, what's our delta y? Well, let's just write in here num steps, and we're going to put that in as 10 number of steps. So delta y here will be the calculation from 5. Okay, let's just correct that a bit more. Let's fix this properly. Right, start y is 5 meters, and in fact that is a, I'm going to colour that in yellow to be a standard. 10 probably also in yellow because that's a standard. We may change it a bit later. And the delta y, the delta that we're going to have is, we'll have to do a calculation. 5 minus yn, 2.4 divided by the number that we're going to do, 10 steps. Okay, is that correct? And that's going to be a distance, a length. We're going to go backwards. We're going to go down in depth. So this is probably a minus, to be formally correct. Okay, and I'll colour that in a beige just so that we remember we've done that as a calculation. Okay, now we can set up to do the integration. So rather than carry on with the integration in this sheet, in this video, which has lasted long enough, I'm going to stop and take a break and do part B, will be the integration setup.